Welcome to the webinar on the CISQ and OMG's new standard for automated source code technical debt. I'm Bill Curtis. I'll be presenting the webinar. I'm the Executive Director of the Consortium for IT Software Quality, or CISQ. We're going to wait a minute because there's still people signing in, and then I'll launch it in about the next minute. Tracy, do I have control?
You do. Do you see it working for you?
Okay. Yeah, let's see if it, where do I? Yeah, okay, good. Now I just have to figure out how to move it forward. Okay.
Try the right arrow. That's basically
yeah.
Okay.
Get this out of the way. Let me begin by just giving you a very quick overview of what the consortium is. It was formed back in 2010 as a joint effort between the Software Engineering Institute at Carnegie Mellon, Paul Nielsen, the CEO there, and Richard Soley, who's the CEO of OMG. Got together. OMG and to some extent SEI were getting requests for some definitions of measures to be taken from the source code of quality characteristics like security and reliability and maintainability for use in contracts, especially outsourcing contracts, because there weren't any international standards that actually dealt with the source code itself. ISO has not been able to get to the level of source code measurement. So they decided to form a consortium. They asked me to be the executive director since I've worked with both organizations. And the objective and the charter really was to define automatable measures of software size and quality, structural quality, that can be measured from the source code, and then put these through the OMG process to become OMG standards. And I'll tell you more about that process in a bit. We originally had 24 members that helped define the original measures. We've gone to a more traditional OMG sponsorship model. And these are the 4 sponsors currently that sponsor OMG's work and the website. They're the ones who are able to participate in the definition of the next round of measures. We've got several more companies that say they're going to join in February. So we may have as many as 4 new sponsors by the end of February. But that's the nature of the consortium. It's a place, OMG is a place where organizations come together, IT organizations, to define the standards they need for basically managing and running their IT operations. I want to start with a definition of technical debt. The original definition, the original development of the debt metaphor was done by Ward Cunningham at UPSLA back in 1992, where he said, look, shipping first-time code is like going into debt. You often have to make decisions that you know are suboptimal, but nevertheless, the goal is to get the code out. You don't really have the time to make the most optimal decision because it would take too long, and the market needs or the company needs the application. So a little debt's okay as long as you pay it back. In essence, you fix it. You fix the problems in reasonable short order. And every minute you spend on not quite right code it counts as interest on the debt. In essence, it's harder and less efficient to work with code that has a lot of technical debt. It's primarily a maintainability issue. It can affect things like scalability, the ease of changing and modifying code, and what have you. As Ward continued to discuss this, basically he was thinking about a strategic trade-off between the cost of shipping suboptimal code and having to come back later and fix it, and the interest, which is basically the excess time you spend working with suboptimal code, versus the business benefit to be derived by going ahead and getting that code into operation, getting it into the market or getting into the company. So the decisions to create a suboptimal design or to suboptimize some part of the code was really this trade-off between knowing you've got to go back and fix it versus the value of going ahead and getting the code out now. Now, over the last 25 years, it's evolved. Industry talks about it a little bit differently. When I talk with CIOs and others in industry that use the term technical debt, most often what they're talking about is lots of violations they have to go in and fix at some point. Now, The Agile Alliance has done some work on describing these different kinds of technical debt. They would call this quality debt. It's the debt you incur having to fix defects and violations of good architectural and coding practice that you know you have to fix. If you don't have to fix it, it really doesn't create a debt. But if you have to fix it in the near term, it does. And this is the way industry most often treats it. The way it's most often talked about in industry is, it's the cost of what I've got to go fix in the future. So basically, it's the correction costs and the interest related to flaws that folks know they must remove. This is the definition that CISQ is working with. We don't claim this is the be-all and end-all of technical debt definitions. There was a workshop in Dogsteel, Germany, almost 2 years ago now, where they got 30 to 40 people working in the technical debt area, doing research in this area. There was a general agreement, especially among the people doing research and academics in the area, that it really was more towards Ward Cunningham's definition, more towards the maintainability issues. They didn't come up with an exact definition, but agreed that that was sort of from a research point of view, their focus. From an industry point of view, what the core request we get most often is to deal with the fact that we really need to be able to estimate what's the cost of going in and fixing these things. So if we work the metaphor out, if we really kind of build out the metaphor, because it's extremely useful, the fact is that industry is gravitating towards this because it expresses software quality in terms that business folks can understand. You talk to a business person and talk about quality, their eyes glaze over. But if we can talk about costs and benefits, then they immediately understand what we're trying to get to, and they can understand the cost issues in having to deal with some of these problems. So when we look at technical debt itself, there's the principle, which is the cost of fixing the architectural and coding flaws released in code that we know we have to remove. So I said earlier, if it's not a critical problem that we don't have to address in the near term or forever, for that matter, then that's not a part of technical debt. It's really the things we know we have to get out of the code fairly quickly because it causes all kinds of problems. It could be a security issue, it could be a reliability issue, it could be a scalability issue. And then as long as those problems are in the code, we have continuing costs in IT. For instance, it takes more developer effort to work on code that's poorly structured. If I've got a performance efficiency issue in the code, it may be taking up extra resources, extra processing time, extra memory. If I'm in the cloud, that's going to cost a good bit of money. So there's all those issues that continue to drive cost beyond fixing until I get this thing fixed. So that's the basic core of technical debt. Now, the nice thing that leads to two other very important issues, which really represent business risk. And the first is, and this is the one that's got the boardroom very concerned now, is liability. What happens if we have a major security breach like Target did that costs in the neighborhood of $200 million? What if we're an airline and have one of these ticketing outages where we can't get people tickets, we can't get them on planes? Some of the recent disasters in the airline industry where people simply couldn't board cost them well over $100 million. I think the one airline Delta cost close to $140 million by the time they got everybody finally on flights, sometimes a day later. So the liability issues right now are way beyond the CTO or the CIO. These have gotten up into the boardroom because of the fact they can affect corporate profits fairly dramatically, and corporate reputation for that matter. And then there's the opportunity cost. The fact that I'm spending time fixing technical debt means I don't have that time to go add new functionality into the application that could drive additional revenue or additional value. So there is an opportunity cost for the fact I leave this in the code and then have to go back at some point and fix it. So this gives us a very nice way to talk about technical debt to the business, talk about software quality and the cost of quality to the business, and the trade-offs we have to make between getting code out now versus fixing it later, the cost of fixing code in the future. So when we look at what management typically wants, and what we're hearing is the value they would get in having a measure of technical debt is, number one, I want a way to predict my corrective maintenance costs, the ones I know I've got to fix in the near future. And so they don't care whether it was an intentional suboptimal design decision or whether it was just a major mistake in a security flaw or reliability problem or a performance problem that was introduced into the code. They don't really care what the foundation of it was. They care that I've got to pay for it and what's it going to cost me to do that. They want a way to compare the applications across a portfolio to identify the ones that are most trouble, because that's going to tell them that's where they're going to have to apply the most resource, especially if it's a business critical application. In many cases, they're looking at old legacy systems and saying, should we try to repair this or replace it? We've actually seen cases where they've evaluated the technical debt in the system and decided that repairing it was going to be cheaper than replacing it, because it wasn't as bad as they thought it was originally once they got in and did the analysis and actually had the hard data on the problems in the system. And another way it's used, although there's a benefit and a danger in this, is evaluating the capability of teams. When the data is given back to the team, when the technical debt issues are identified, often the team learns. They can use that to prioritize what they need to fix. So it's used for improvement, either of the team's performance or of the product. There's a benefit. Teams actually sometimes like that data. They want that data because they know it tells them what they need to go work on and some mistakes they might have made they didn't understand. However, if this ever gets into HR decisions like raises and performance appraisals and the like, it'll destroy the system because developers are too smart not to figure out how to game these things. So the goal here is to use this for improvement, either of the team's performance, where the team uses the data to learn about the kinds of mistakes they make, or to make priorities about how they need to improve the product itself. So these are the major uses, which is why CISQ chose the direction it did in creating a technical debt measure specifically for helping these kinds of uses. So it's not just the classic Ward-Cunningham definition. We're actually expanding it a bit beyond what many in the research community would prefer, to really cover the problems that we know we have to fix in the code, because that addresses most of these kinds of issues. CISQ is going to has built this standard for technical debt out of existing measures it had already produced and that have been approved as standards of the Object Management Group. When we formed CISQ back in 2010, we had meetings. We had executive forums in Washington, D.C., Frankfurt, Germany, and Bangalore, India. We invited the executives to come and tell us what measures they would most want us to work on if we, in fact, went ahead and formed CISQ. And we went through a voting process, and consistently across those three meetings, you see there the 5 measures that were the most popular, the ones they really wanted us to address initially. They wanted a measure for automated function points, and they wanted measures for 4 quality characteristics. You can see those there: reliability, performance, efficiency, security, and maintainability. So we spent a couple of years. Automated function points was the first one that was approved in 2013. The other 4 were approved over the next couple of years, so about the end of 2015, early 2016. All of these had been approved as standards by the OMG, go into their list of standards. You can get them for free off of the OMG website. They're also available on the CISQ website, and I'll show you that address at the end of the briefing. We've started submitting some of these over to ISO. In fact, automated function points has already been submitted for consideration by ISO. And we're holding deployment workshops currently in the U.S. and in Europe. We'll probably expand that possibly to India this year. But these are major workshops and seminars and conferences where we actually bring major speakers together and describe the metrics, and then talk about the general issues and things like cybersecurity and modernization of systems and what have you. We're holding one in Washington, D.C. in March. I'll show you more about that on the final slide. This is how we built the CISQ measures, the 4 quality characteristic measures. We made sure that these were consistent with the definitions of these quality characteristics in ISO 25010, which is the standard that defines the ISO software quality model. We're revising that currently. I'm one of the co-editors of the revision. But it'll be reasonably consistent with what is already there, and the CISQ measure will be consistent with the new revision. We formed these measures out of known weaknesses that were critical, that were weaknesses you had to remove, that most people participating, the 24 companies participating in the development of these original standards, all or mostly agreed that these were the weaknesses that had to be removed from the code. So you can see the number of weaknesses in each one of these. In the area of security, there was already an existing list of what the industry considered the worst weaknesses. They're the top 25 common weaknesses, CWEs, common weakness enumeration. That's the SANS Institute top 25, the OWASP top 10. And we just adopted that. We said, well, there's 22 of those that you can detect with static analysis. That became the security measure. In the other cases, we spent about a year going through lots of different weaknesses and looking at what really was critical and what wasn't to define what those measures were. So the actual measures are simply a count of the number of weaknesses in the code. You can then divide that by function points or lines of code or any other size measure to get a density measure, or do various other transformations of this basic measure into useful measures. Now, these are examples of the violations in each of those measures. So you see in SQL, in weak security, be SQL injection, cross-site scripting, buffer overflows, and maintainability, things like dead code, excessive coupling, hard-coded literals, and what have you. So these are known problems that can cause serious issues in reliability or maintainability that at some point you probably need to remove from the code. The technical debt measure was built on top of those. Since we already had a list of the violations that were critical, that the people that defined those measures, the companies that defined those measures, felt like those had to be removed from the code. We then said, let's just build this measure on top of that because it gives us a correlate of the overall corrective maintenance effort required to fix these structural quality problems that are going to have to be addressed at some point. So we took all those are the violations that form the technical debt measure, and this is a large component ultimately of the cost of quality, which is something obviously that concerns IT executives. So let me show you how we calculate this measure. We took each of the 86 violations included in the CISQ measures. We got a large number of developers. We asked them, how long would it take you to fix this defect in the simplest case? In essence, it's in a well-coded component or several well-coded components. They're not highly coupled to the system. How long would it take you to fix this? So that became the default hours. And there was more variation than I thought there would be in the answers, but we tried to sort of take the expected value. And this is an area we're going to have to continue collecting data in and may revise some of these default values as we get more data. Primarily, we were taking this from folks working in Java and .NET. If you're working in C and C++, it might take longer. If you're working in COBOL, heaven help you, it may take longer as well. So, but these are the default hours. Now, there is a way to correct this. We built in adjustment factors that come out of analysis of the code, that can come out of a good static analysis of the code. For instance, the structural complexity of the components, the component, or if it's a a multi-component defect, the complexity of the components involved. And this is things, in things like, includes things like the cyclomatic complexity and other things related to the complexity inside a component. In addition, there's the exposure of that component to the rest of the system. So how far could that defect propagate its effects? Because you're going to have to go check those out to make sure you don't have unintended side effects when you make a correction. So that's another adjustment factor. If it's a multi-component defect, some of those components may be in a different part of the application, in a different layer, written in a different language. That's going to create more time and effort to fix it because of the several languages you may have to work in to create the fix. If there's a number of weaknesses in the same component, then actually the time for each subsequent fixing each subsequent defect will go down because you won't have to relearn what's in the component. So that would be an adjustment factor that actually reduce effort over time as you continue to fix severe defects in that component. In addition, some of these defects involve a threshold. If it's more than X, then it's a violation. If it's less, it's not. And so we look at the gap between the threshold and the higher number to see how many more things you're going to have to fix or how much more effort it's going to take. So that allows us to adjust the default hours. If in fact you think in your situation the default hours are a bad representation of the fixing effort, you can change it. That's always available. You don't get the benchmarking capability because you're going to be different from what the standard was, but that's okay. If it fits your ability to predict defects or predict maintenance effort better and corrective maintenance effort better, that's good. So once we get for each, and we do this for each individual weakness and each instance of a weakness. So if I've got, let's say I've got a number of places where I've got an expensive operator inside a loop working on a very large table, it's going to really slow down the system. I'm going to go look at each one of those and calculate the adjustment factors for that, if each instance on that instance to get an adjusted effort for that instance. Then I can add those up for that weakness. All right, so in this case, I'd be adding them up for all the instances of expensive operators inside loops. And if it's useful, you can give a technical debt measure related to that weakness. I don't know that too many people would use it that way, but it's possible. So that's the adjusted effort, the total value of the effort for having to fix that particular weakness. Now, in each of the quality characteristics, reliability and security, I can add all of those weakness efforts up and get an overall technical debt for that quality characteristic. So if my interest is, what is it going to cost me to fix all the serious security violations in the code, I can produce that measure, technical debt measure related to security or related to maintainability or any of the other measures. And then I can sum all that up at the higher level across the 4 quality characteristics to get an overall technical debt measure for the application. Now, this is based on the CISQ measure, the standardized CISQ measures for quality characteristics, security, reliability, performance efficiency, and maintainability. So this is a specific technical debt measure related to the CISQ quality characteristic measures. Again, we make no claim that this is the perfect measure of technical debt. What it is a useful measure. It's a useful measure for doing some of the things we've heard IT executives, IT application managers want, which is the ability to predict corrective maintenance cost, the ability to evaluate the quality of the applications in their portfolio so they know where they're most at risk, and other kinds of applications. So it does give us a useful measure. It's not the be-all, end-all. It's not the perfect measure, but at this point, it's a useful measure. And as we move forward, OMG has a very effective mechanism for revising these measures. So as we find more weaknesses that need to be added in or some that aren't as important and ought to be removed, we can do that. As we get better data on the default hours to fix a violation, we can make those changes as well. So this could evolve as we get more data and the measures get used and we get more real experience. We can feed that back into what OMG calls a revision task force to make revisions and improvements in the measures that they have produced as standards. So how does this fit into the overall picture? Right now, these 4 dark boxes represent standards that CISQ has produced through the object management group. There's the 4 quality characteristic measures there at the bottom, and their collective building into this automated technical debt measure. You see at the top, we've got the size measure, automated function points. There was a need to get a measure that was like function points, but also included non-functional code that had both functional and non-functional to give us a fuller representation of the size of an app. So we created this concept called automated enhancement points, which is now an OMG standard, and it's available commercially. And we can take automated enhancement points, the size measure, and automated technical debt quality measure, and come up with this concept of quality adjusted productivity. In essence, technical debt really, the effort, if you created technical debt in this release or in this sprint, then you ought to be charged the hours to fix it against the productivity in this sprint. I mean, we push that off to a future release or a future sprint to fix. And there we often treat that as new work. We give ourselves credit for the amount of efforts or the amount of lines of code touched and the effort. We treat that as productivity. We shouldn't. It's just waste. And a concept of lean Anything you do to fix defects is total waste, and you should get no productivity credit. In fact, it should be charged back against your productivity in the release or in the sprint where you created it. So that's the concept of quality adjusted productivity. We look at the critical violations or weaknesses we created in this sprint or this release. We estimate the effort to fix it in the future, and we charge it back against the productivity of this particular release. In addition, the 4 quality characteristic measures have been primarily defined for business or IT systems. And so we have an effort starting this year, it starts in February, to extend these into embedded software, into embedded real-time systems. And we have a couple of companies joining that have expertise in real-time systems. One's a defense company, a defense aerospace company. They're very interested in having this. This also is very important when we move into the Internet of Things, where you've got embedded code interacting with a more classic IT application. So that's an effort we're going to put together this year, and hopefully by the end of the year we have definitions of extensions to the existing quality characteristic measures for those specific kinds of weaknesses that come up in embedded real-time systems. So that's the roadmap of where we are and where we're going in the future. And the last slide here is the CISQ website. I encourage you to go there. You can become a member. Membership is free. That's why we have sponsors. They cover the cost required to maintain the website, to hold these conferences, and to do the other things that CISQ does. You can just see the nice lady up there. Go there and push the member button right below her, and we'll ask you a few questions, and we'll send you a password, and you're in. The standards are there. They're free. There's descriptions of how to use them in contracts. We're already starting to see some government agencies list some of the CISQ measures as things they would use in contracts. The French government has determined that they will require all future sizing on contracts they support to be reported in automated function points, because that at least gives them a consistent measure, consistent, reliable measure. And so we're starting to see them being referenced in a number of, especially U.S. government acquisitions. So it's, we're really at the very beginning of the adoption of these measures. And as we move forward, these will become more important. We'll have more information here. All of the presentations at our previous seminars are there. Some of these are by very senior government officials and places like NIST and Homeland Security and the Department of Defense, NSA. We've had some in Europe as well, at one in Europe we had last year. So those presentations are available in the area of cybersecurity, in the area of IT modernization, and how to use measures to guide these efforts. You see there at the bottom, our next summit is going to be in Washington, D.C. on March 20th. We invite you to come. It'll be in Reston at the OMG meeting, and we'll be lining up some senior government and industry folks to make presentations on issues in modernization, in cybersecurity, and other related topics. So let me hold it there. We don't have really much time for questions. If you want to submit questions, that's okay. We'll do our best to get them answered in a reasonably short period of time. Let's see. I see one question up here. It's hard to read these things. Well, the presentation is available. Actually, you can see, I think we have there on handouts. If you go down to the handouts, you'll see there's two handouts. One is this presentation. The other is the announcement of the Cybersecurity and Modernization Summit that we're going to hold in March. So you can download those two things. If for any reason you can't get it from there, email us, Tracy, TRACIE @omg.org, and our program manager, Tracy Berardi, will be happy to send you those. Let's see, there's another question here. To itemize the top 20 to 30 weaknesses in each of the 4 CISQ quality measures, it was mentioned some of them were borrowed from ISO 20. No, the measures weren't borrowed from the ISO 25010. We made sure that these measures, that our definition of the measure was consistent with the definitions in 25010. The actual measures, ISO software quality measures, are in ISO 25023. The problem is they never got down to the level of source code. There's only 2 out of the 50 or 60 measures that actually deal with source code. And so what the CISQ measures do is supplement ISO 25023 by taking the OMG quality model in 4 areas and moving that down to the source code level, moving the measurement down to the source code level. So we supplement ISO 25023, and we're consistent with the quality characteristic definitions in 25010. So we've tried to maintain that consistency. We're on 25023, but to date, I've not been successful in getting them to the source code level. We will have to revise that as a result of revisions of 25023, and we're aware that it's weak in the area of internal structural quality, and I'm going to try to get us to address that more effectively in the 25023 revision. So we're at the bottom of the half hour. Let me close the webinar now. We'll take these questions and produce some answers and ship them out. So thank you for your attending. I hope this has helped you understand this better. There's a number of places that have done a lot of work in technical debt. The SEI is one. Robert Nord, Rebecca Skyat there have done a good bit of work in this. Philip Cruckton at the University of British Columbia has done a lot of work. There's a number of other people that have done a good bit of research and formulation in the technical debt area. And I refer you to kind of look at those websites and others, and if you're interested in this topic, to get more depth. This is the approach we've taken in CISQ. It's primarily to serve some specific interests in industry, but it is a different approach from the classic technical debt approach that Ward Cunningham formulated, because we're trying to provide measures with specific objectives of helping improve the ability to predict corrective maintenance efforts and therefore corrective maintenance costs. So thank you very much, and wish you a good day.